Hello everyone, welcome back to our Vision Transformer series. In this second video, we'll delve further into the world of self-attention in the visual domain. We'll explore three key papers that effectively utilize self-attention mechanisms for image processing. So let's dive in. Let's step back and compare the evolution of attention mechanisms and transformers in both NLP and vision domains. In NLP, we started with deep learning models based on RNNs. Then the attention mechanism emerged as a component of RNN models. Eventually, the transformer model arrived, introducing self-attention without relying on RNNs. In the vision field, traditional models initially relied on CNNs. Subsequently, some approaches began to integrate both convolution and self-attention together. This was followed by the development of standalone self-attention models. Ultimately, the vision transformers or VIT emerged, representing a significant advancement in the field. We started this series with the non-local module in our previous video. Today, we will continue our journey and we are focusing on attention-augmented convolution and two influential papers on standalone self-attention. This will help us understand the progression of attention in the vision domain, setting the stage for VITs or vision transformers, which we'll explore in our next video. So here is our first paper titled Attention-Augmented Convolution. It presents an innovative approach. Rather than abandoning convolution entirely, it merges convolution with self-attention. This hybrid method harnesses the strength of both worlds, the local connectivity of convolution and the capacity of self-attention to model long-range dependencies. Let's delve into the formulation of attention. We start with the input tensor x, which has the dimensions h times w times f in for height, width, and the number of feature maps or channels. This is a three-dimensional tensor, excluding the batch dimension. First, we reshape this tensor into a two-dimensional form, so that is hw times f in. For a single head's attention output is determined by the softmax equation, a concept that we are already familiar with from our previous discussions. After that, multi-head attention combines the outputs from these different heads. However, there is a catch here in this formulation. This is permutation invariant. That means if pi is a permutation over positions, then MHA for multi-head attention of pi of x is equal to pi of MHA of x. Due to this characteristic, it's not as effective for structured data such as the sequences or images, where the arrangement and order of data are crucial. So to tackle this issue, we use position embeddings to enhance self-attention with position information. When designing these embeddings, having these two properties are ideal, preventing permutation equivariance while enabling translation equivariance. Given these requirements, the authors opted for relative position embeddings. I have already discussed relative position embedding or RPE in detail in another video. You can find the link in the description. So let's quickly recap what relative position embeddings entail. Absolute position embeddings rely on the absolute indexes of tokens in a sequence, starting from 0 and going up to the sequence length L. In contrast, relative position embedding focuses on differences between two positions, I and j, where I is the query index and j is the key index in the self-attention equation. This gives us an embedding vector R of j minus I for the relative position j minus I. When calculating attention scores, we now have two terms. The standard attention score, which is Qi transpose Kj, and the relative attention score given by Qi transpose R sub j minus I. These two terms are combined, scaled, and then passed through a softmax function for normalization. In adapting relative position embeddings for 2D images, the authors expanded the concept from a 1D sequence to a 2D format. This involves considering relative positions along both the width and height axes of an image. For instance, if we look at elements I and j in this diagram, we calculate the differences jx minus ix as well as jy minus iy along these axes. To achieve this, separate learnable embedding lookups are used for each axis. This gives us two embedding vectors Rw for Jx minus Ix as well as Rh for Jy minus Iy. Consequently, we now include two relative attention terms in the self-attention calculation, each corresponding to the width and height dimensions of the image. The proposed attention-augmented convolution is showcased here, featuring two parallel branches. On the bottom, we have the convolution branch, and the top branch is the multi-head self-attention branch with nh number of heads. These branches are then merged with their outputs concatenated together. This combination is followed by a one-by-one convolution, which effectively blends the feature maps from both convolution and attention processes. Next, we will delve into how this approach can be used to modify the ResNet architecture. Here we have the original building blocks of ResNet 34 and ResNet 50. To quickly recap, ResNet 34, shown on the left, features repeating residual blocks, each with two 3x3 convolutional layers. ResNet 50 on the right includes a different setup with two 1x1 convolutional layers and a 3x3 convolutional layer sandwiched in between. So this is known as the bottleneck block. In creating attention-augmented ResNet, the key is to maintain the 1x1 convolutional layers intact while augmenting all the 3x3 convolutional layers with attention mechanism. So let's move on to see how these architectures are altered with this augmentation. On the left is the original residual block in ResNet 34, and after augmenting that, we get the attention-augmented residual block as shown on the right. The key difference is that the augmented block, the 3x3 convolution layers are paired with a parallel attention branch, and their results are then concatenated as we discussed earlier. Similarly, for ResNet 50, the residual blocks have undergone a comparable modification, and the augmented block shown on the right incorporates these changes. So this concludes our overview of the first paper. Next, we will move on to our second paper, which delves into the realm of standalone self-attention in vision. This paper replaces all spatial convolutions with attention and builds a fully attentional model. So let's see how it is done. As we have previously discussed in another video, the standard scaled dot product attention has quadratic complexity, which makes it less practical for high-resolution images. Therefore, the authors decided to use local attention. In local attention, we first build these local regions called n sub k with extent size k that is centered at position ij as shown in this figure. Now, in the local attention mechanism, output yij is computed as the sum of the softmax of qij transpose kab for all ab positions in that local region. And here is the diagram of the local attention. Note that for the output yij, the query vector qij is represented by a single vector, but in contrast, the keys and values are structured as a matrix corresponding to all positions within that 2D local region, which is centered around ij. But there is more to the story. We also need the relative position embeddings in the attention mechanism because, as we discussed previously, the attention by itself is permutation invariant. So here, the authors used 2D relative positions in the local region as shown in this example. And the relative position scores qij transpose r sub a minus I b minus j are added to the standard attention scores. Now let's explore how to integrate this local attention mechanism into the ResNet architecture. The paper treats the stem layers, that is the initial layers of a CNN, different from the non-stem layers. So for the non-stem layers, we can replace the 3x3 convolutional layers with the proposed local attention, as it is illustrated on the right. It's important to note that the distinction in this approach from the previous paper. While the previous paper retained and augmented the 3x3 convolutional layer, this paper is completely replacing them. Regarding the stem layers, it's crucial to understand their significant role in capturing key features that the later layers utilize. In the ResNet architecture, the stem layers consist of a 7x7 convolution followed by a 3x3 max pooling layer both having a stride of 2. The paper acknowledges that self-attention mechanisms face challenges in effectively capturing features within these stem layers. So to address this issue, the authors propose applying additional linear transformations. These transformations are designed to enhance the capability of the self-attention mechanism in these initial layers, ensuring that they can capture the essential features effectively. Our final paper in this video is Axial Deep Lab, which introduces a standalone attention mechanism based on the axial attention. For addressing the issue of quadratic complexity in the attention mechanism, this paper presents a shift by adopting axial attention. Axial attention deviates from applying a full attention span across the entire image. Instead, it employs two separate 1D attentions along the width and height axes. This method effectively bypasses the problem of quadratic complexity associated with traditional attention mechanisms. Regarding this issue of permutation invariance, similar to the previous two papers, this one also utilizes relative attention. However, the approach here involves using relative position embeddings for queries, keys, and values. For the output corresponding to the query at position O and iterating over possible positions P along the two axes for key and value, the embeddings are denoted as RQ P-O, RK P-O, and RV P-O. Consequently, the attention equation is updated to incorporate these relative position embeddings, enhancing the model's capability to handle structured data like images. Finally, let's explore how the ResNet architecture can be modified using this axial attention mechanism, resulting in what we call axial ResNet. For the non-stem layers, the traditional 3x3 convolutional layer are replaced with the newly proposed position-sensitive axial attention. As previously discussed, the stem layers are crucial for initial feature capture. Recognizing their importance, this paper chooses not to alter the convolutional process in the stem layers. Therefore, the convolution in these initial layers remain intact, ensuring that the fundamental feature extraction capabilities of the ResNet architecture are preserved. And that concludes our video. In summary, we have reviewed three significant papers: attention-augmented convolution, standalone self-attention, and standalone axial attention. Each of these papers propose modifications to the ResNet architecture, reflecting the evolving landscape of deep learning in image processing. Throughout this video, we have highlighted key challenges in the domain of attention mechanisms for images, such as the quadratic complexity and permutation invariance. We have also explored the diverse approaches that these papers have taken to address these issues. Looking ahead, our next paper or our next video will delve into the vision transformers or VIT, providing a comprehensive exploration of its intricacies and applications. Thank you for watching, and I look forward to continuing this journey with you in our upcoming video.